Welcome back to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep from IIT Hyderabad. Let's have a brief recap of what we were discussing the last time around. We saw the different technological and commercial aspects of PC RAM technology. We saw first that the PC RAMs can be tuned across two different verticals. First, we can play with the materials composition that helps us tune the crystallization temperature of the phase change material, thereby influencing the set latency and reset current. Next, we saw how the two design principles of having first a small programmable volume and also thermal management guidelines is the key aspect of designing an optimized PC RAM cell. Also, we saw how excellent multi-bit performance and endurance up to almost 10 to the power of 8 cycles is possible through different pulsing mechanisms in the PC RAM cell. However, the scaling challenges of PC RAMs were really very dominant. They were of thermal crosstalk and having an access transistor which can supply the large reset currents which are necessary to change the device from low resistance state to high resistance state. And therefore the access transistor also needs to be very big, and this is what limits the scalability of PC RAMs to roughly 20 to 40 F squared. And this limitation was reflected in the commercialization trends, where a lot of companies have introduced PC RAM products but later found it very difficult to compete with NAND flash in terms of both high bit density and also because of the troubles of cost per bit. Okay, so today we are going to start our third part of sixth module, which is on RRAMs, and we will spend a little bit more time in RRAMs. That is because, at least in my perspective, RRAMs are possibly the most promising candidates for commercialization, especially in the context of filling this so-called memory hole between the DRAM and your NAND flash, which is to be accommodated by storage class memories. Therefore, one reason for spending a little bit more time in RRAMs is this promise for a larger possibility of commercialization. The other reason is that the intrinsic mechanisms that are involved in RRAMs are a bit more diverse compared to other eNVMs. So we will see that as we go along. So first and foremost, what is an RRAM? So first we will look at the basic structure and operation, generic structure and operation, and we will see how is it different from other eNVMs. So as you can see in the slide, I have written that a two-terminal non-volatile memory. The non-volatile memory is very important. So we are calling it a memory because the switching speeds are very high and the latency is very low. And also you can call it a storage element because, as we will see, the bit density is quite high. And that works through modulating the resistance of a dielectric material. Now, you may raise an objection here that even FE RAMs or PC RAMs also have a dielectric material, and the resistance of the dielectric material is what gets modulated. In PC RAMs, you see you have GST, which is like a dielectric material, and you keep changing it from amorphous phase to crystalline phase. But remember, in PC RAMs and in FE RAMs, this material, this dielectric material has certain special qualities. Like in FE RAMs, it's a ferroelectric. In PC RAMs, it has phase change properties. But in the case of RRAMs, the dielectric that we are talking about is a normal paraelectric material which does not have any special properties. What is a normal paraelectric material? Whose polarization versus electric field is linear. But something will get modified in the dielectric, the property of the dielectric material, which will make it a conductive material, and it will modulate its resistance. So generally, the RRAMs are vertical structures of metal insulator and metal sandwiches. So you see, you have a metal which is called also the top electrode. This is insulator and this is called metal, which is the bottom electrode. Why is it called top and bottom electrode? This is because generally our ramps are structured in a vertical fashion. Why are they structured in vertical fashion? As we will see, it is because of area and both voltage and power scalability. Why in terms of area scalability? Remember, for the same reason, we started preferring vertical cell structures in PC RAMs also, because it is much easier to make a very thin dielectric through thin film deposition techniques like PVD or ALD is much easier than to pattern lithographically to metal contact side by side. So if you had to make a lateral device and you had to make it very scalable, means the area should be very less, you have to focus on lithography. Now doing lithography in the nanometer scale, 5 nanometer, 10 nanometer is quite challenging. But to deposit a thin film of 5 to 10 nanometers is relatively easy. That is the first thing. This also leads to the answer of voltage or power scalability. The smaller we can make the dimensions of this insulator will be the voltage for operation, because electric fields is voltage divided by this distance d. So if the distance is low, the voltage can also be low to facilitate electric fields of reasonable magnitude. Okay, so this what we have constructed or illustrated in front of you, a vertical MIM structure, is the so-called virgin device or as fabricated device. So this terminology of virgin device comes from your fuse terminologies. Remember, when we were introducing to you at the beginning of NAND flash the programmable read-only memories, PROMs, we saw that programmable read-only memories also constitute of metal insulator metal structures which are one-time programmable. So a natural question would be, if that was also an MIM structure, how are fuses different from our RAMs? And this is what we need to ask. So both are MIM structures, are MIM capacitors, but they are functionally different. The functional difference first comes in the fact that in an MIM capacitor, you do not want any degradation of this oxide to happen. A capacitor is supposed to work such that there is no leakage happening through the two metal contacts. But in an RRAM device, you want to create elements which switches from high and low resistive state. The same is the case with read-only memories or programmable read-only memories. But in programmable read-only memories, remember, since you were able to do the write only once, that means either a fuse is in open condition or it is in fused condition, which is the closed condition, that happens, that programming only happens once. That is why it is a read-only memory. But RRAMs are storage elements that you have to keep switching from open and closed configuration, or high and low resistance states have to be repeatably switchable. That is what makes your fuses functionally different from your RRAMs, although they may be structurally the same. And this brings us to the most important step, or the first step of converting this MIM structure into a useful RRAM device. And this step is called the forming step. So what is this forming step? This forming step is a one-time process which is not always needed, but generally needed in most of the RRAMs. And the job of the forming step is to create something called a conductive filament. Now what is a conductive filament? Conductive filament is finally the main functional element of the device, which either will get created or annihilated to give you low and high resistance states respectively. So how is it different from a fuse? In a fuse, you do not really care even if this conductive filament is permanent in nature, because it is only one time programmable. But in RRAMs, you have to create a controlled filament. So what is the meaning of a controlled filament? the objective and meaning of a control filament is that which can be created and annihilated several times. So you do not want a permanent damage in the case of RRAMs. And this explains the general operating principle or mechanism of an RRAM. It consists of this controlled filament either in dissolved state, and at that time it is in high resistance state because between the top electrode and bottom electrode there is no electrical contact, therefore because the filament is dissolved and therefore it is in high resistance state, or it can be in the state that it has already formed. So from formed state to dissolved state you switch from low resistance to high resistance, and when you can do this repeatably with high endurance back and forth, that is the key criteria here. When you can repeatably do it back and forth, then only you can call it an RRAM device. Okay. Now, depending on what is the nature of this conductive filament and how this process of dissolution of the filament and formation of the filament happens, your RRAMs are broadly divided into two categories or two subclasses, and that is what we will see a little while later. Before that, as we have been doing, let's look at a brief historical review of how these common MIM structures were transformed into RRAMs. So the first concept of resistive switching was shown in GE labs by the scientist called Hickmott in 1962, where he saw using direct current DC measurements, there is a sudden change in the resistance of oxide films under a particular bias. And these oxide films, he was able to observe very nice switching because he had made these oxide films very, very thin, or in the order of 35 nanometers, 40 nanometers, or even 100 nanometers. Now, those in current day context look very large, but in 1962s, making these thin films was a novelty. So what Hickmott basically showed is, maybe it's not clear from this diagram, when you sweep the device, it goes in a high resistance state and suddenly something happens in the device and it is now able to switch in the low resistance state. So the direction of sweep is from here to here and then back over here. So earlier the device was in high resistance state, that is expected because oxides are insulating materials, and something happens at some critical electric field such that the conductance of the system suddenly increase and now you are back in low resistance state. But at that time, although they had shown it for many different compounds such as oxides and chalcogenides, the exact mechanism was not really known. Okay, there was renewed interest in the 1990s in resistive RAMs because to make scalable memory devices is a challenge, and that is why there was renewed interest, and HP Labs was the first who began on TiO2 based switching devices. Okay, so as we know and we have seen, HP Labs were the first to demonstrate resistive RAM devices more systematically and correlate it to Leon Chua's memristor concept, which was discovered in 1971, and that was a great breakthrough because for the first time they were able to show not just resistor switching from high resistance to low resistance but back and forth several times, and they had a consistent theory to explain it. Since 2010s, RRAMs have been very popular and several material systems such as perovskites, hafnia, tantalum oxide, nickel oxide all have been explored in lot of depth, and even your big companies like Panasonic, Sony, Micron have taken lot of interest in RRAMs and switching of RRAMs because they are really important candidates for filling the elusive storage class memory gap. Very interestingly, in the context of our course, in 2020s, it was realized that RRAMs could be the leading candidate in emerging eNVMs with special interest not just in embedded memories but for analog computing and AI accelerators. Let me not discuss too much about it right now because in the final part of our course, we will be discussing how RRAMs could really make a very important role in AI ML computing, especially analog dot matrix product accelerators. So I'm just giving you a teaser. We will discuss much more in detail. And so it begs the question, why are RRAMs so popular? What is the reason that they might be most suitable for commercialization? And we will do this by comparing your RRAMs with your traditional flash memories and other promising candidates of SCM such as PCRAM and MRAM. So the first thing that we would want to note is the area scalability and the device scalability. So when I mean footprint is if I have a minimum feature size of F, what is the area of the cell? And as we have shown even in NAND flash, that the theoretically lowest possible cell size is 4F squared. And this is very much possible in RRAMs because of the simplistic nature or the facile nature of the RRAM structure. As you can see, if you can make something called crossbar arrays, for the first time we are introducing crossbar arrays. What are crossbar arrays? These crossbar arrays are nothing but word lines which are your top electrodes. You see, these are your word lines which are going in this particular direction, and your bit lines which are going in this particular direction. Only if you sandwich an oxide material or a simple dielectric material which can be easily deposited by any of your CMOS compatible processors, the promise is that there will be a very dense form of array. This is because at the cross point of bit line and word line with very low footprint, you can create individual memory devices. So that is the key promise, that with just 4F squared and dense crossbar structures, you can have very high bit density. Not only that, it is also important to mention the point about device scalability. Device scalability is how small can you make the smallest feature size of F. And we have already seen in the previous slide that the difference between RRAMs and other eNVMs is RRAMs are mediated by these single or multiple filaments. Now the smaller you can make the size of the filaments, which is generally in the order of nanometers. The cross-sectional area of the filaments is generally in the order of few nanometers squared, and that is what determines how small F can be. And therefore RRAMs have very good both footprint, scalability and device scalability. The next important part is to look at speed. How quickly can you form and dissolve these filaments? Although there are some reports which shows that these can happen even in the order of 300 picoseconds, which is comparable to, remember, your SRAM cells. But normally people report that generally RRAMs can switch at the speed of less than 10 nanoseconds. Now remember, this is much better than your flash, and it is also much better than your PC RAMs. PC RAMs, you need hundreds of nanoseconds during the set cycle. However, it is still not as fast as MRAMs, but MRAMs have some other issues that we will discuss very soon. The other important thing is to look at endurance and retention. Here too, we see that the endurance and retention of RRAMs is much better than NAND flash. So as you can see, the endurance can go as high as 10 to the power of 10 cycles, which is almost 4-5 orders of magnitude higher than that in flash, and around 2-3 orders of magnitude higher than PC RAMs. Also, the retention of these filamentary RRAMs is very good. It is showing 10 years, which is the industry standard for proving non-volatile memory at 85 degrees Celsius. This is better than flash and almost comparable to PC RAMs. The fourth important point to look at is the switching voltage and also the switching power. As I have shown in RRAMs, by controlling the thickness of the oxide material by making it few nanometers thin, 5 nanometer, 10 nanometer thin, you can substantially reduce the operating voltage of these RRAMs. As a result, it has now been demonstrated that RRAMs can operate even at femtojoules of. Now, this is much better than your flash memory, and it is also much better than your PC RAMs. In PC RAMs, your reset process, which requires a lot of current, is what limits switching power, but definitely what is theoretically possible in MRAMs at least is better than femtojoules, but that has not been practically realized yet. The other important aspect is ability for multi-bit storage. As we will see, by using different strategies, it is possible to accommodate multi-bit functionality in RRAMs. And this is very, very crucial for not just your digital computing. Why? Because your area scalability becomes much better. Remember, even in NAND flash, your 4f squared becomes 4f squared by n. The logical bit scaling becomes much better when you are able to have multi-bit storage. This is one of the aspects, but RRAMs are more useful for probably analog neuromorphic computing. And as we will see, the behavior of synapses is something which has several closely spaced analog weights, and it turns out that RRAMs could be an excellent candidate to demonstrate the same. The final point which I have marked out is the reason I think why RRAMs will probably beat other eNVMs in becoming most commercially viable, and the reason is that all the steps that are used in RRAM processing, especially the deposition of the oxide and the top and bottom metal electrodes, are entirely CMOS compatible. In fact, you will see the oxides that are generally used in RRAM technology is the same as the gate oxide of your transistors, or even the oxides which are used to line your capacitor in your DRAM technology. So, as you know, having borrowability from established processes is very, very good, because one of the reasons that PC RAMs did not do very well commercially was because all the processes were not very, very CMOS compatible. That led to very large cost per bit, and the same is the case with MRAMs also. In this regard, because cost per bit is a very important metric when it comes to commercialization, I believe that our RRAMs will beat all the other candidates in storage class memories. Not only that, these CMOS compatible oxides can be grown at back end of the line compatible temperatures. What is the meaning of back end of the line compatible? It means it can be deposited even after the basic front end of the line logic processing is done. And so it is very easy to integrate front end of the line transistors with back end of the line RRAMs. This gives you very interesting functional integration along with very good dimensional integration. This is something that we will discuss a little later. However, it is important to know that there are several challenges also in RRAM integration. It is not always a very rosy picture. There are challenges in crossbar integration, in reliability issues such as variability, especially in the multi-level operation criteria. So there are these challenges. We will discuss what these challenges are and how we are trying to mitigate them. A bonus point is something that we in our research group also focus on, as we will see that there are inherent variability associated with how these filaments in RRAMs form and dissolve. Can we use these variability to our advantage for hardware security applications, for random number generator, for stochastic computing, is also a very interesting possibility that people are exploring. Okay, having understood the importance of RRAMs, let's do a deep dive now. Remember, your RRAM was your two-terminal non-volatile memory, which operated first by the formation of this controlled filament, and then the operation mechanism was this back and forth switching through dissolution and creation of these filaments. As we had also discussed that depending on the nature of the conductive filament and their operation mechanisms, there are two key subclasses of RRAMs. So we will discuss what are these two subclasses of RRAMs and we will conclude today's lecture. So as we have already defined that memory or bits, especially at multi-level, are somehow stored through the creation and annihilation of these conductive filaments. Now, depending on the nature of these conductive filaments, RRAMs are divided into two main subclasses. One is your VCRAM or your valence change random access memory, and other is called CBRAM, which is also called conductive bridge random access memory. So let's begin with VCRAM first. Before we begin with VCRAM, it is important to note for historical reasons, earlier VCRAMs were also called OXRAMs, where OX stands for oxides. This is because the first generation of VCRAMs only had oxide as the insulating or dielectric material, but now it has been shown that this is an obsolete term because similar things can be shown for other compounds which are insulating as well. So first let's look at the structure of your valence change RAM. So the structure of your valence change RAM, just like your normal RRAM, consists of a top electrode and a bottom electrode, but there is some speciality in the top and bottom electrodes. Both the top and bottom electrodes consist of so-called noble metals. As you might have studied in your basic chemistry, noble metals are those which do not ionize or oxidize very easily. In terms of electronic band structure, it is something which has very high work function. So some of the common noble materials which are used for making VCRAM's top and bottom electrodes are gold, platinum, palladium and also nickel. What is the insulating material? The insulating material is generally an metal oxide of the form MOX, where M most of the time is a transition metal like hafnia, titania, tantalum, so on and so forth. But also other materials like aluminium and silicon are also used. As I had said, because the first generation of VCRAMs were based on oxide materials, they are also called OXRAMs, but this insulating material can also come from chalcogenides, nitrides and other compounds. Next thing that we will look at is what is the composition of this filament that connects the top and bottom electrode, which makes the system go from a high resistance state to a low resistance state. And the nature of this filament is valence changed, substoichiometric in the metal oxide. So these are generally oxygen vacancies in the context of a oxide film. So as you may know, a metal oxide, when the stoichiometry is complete, shows insulating behavior. But when the stoichiometry is modified or the valency of the metal oxide has been changed by making it oxygen deficient, it has been shown that the region which has substoichiometric oxide starts behaving in a conductive manner. And that is the fundamental reason for this filamentary formation. So how does this metal oxide get transformed only in localized regions to substoichiometric filaments? That is something that we will see in the next class. But it is important to know that valence change RAMs are based on two further subdivisions in the mechanism of formation and dissolution of this substoichiometric oxide filament. That is electrochemical, which is an electric field driven process, and thermochemical. As the name suggests, it is a thermally driven process. So VCRAMs, the filament is a substoichiometric valency changed material which transforms only a small area, which is known as the filament, from insulating to conductive, and this can happen either electrochemically or thermochemically. Moving on to conductive bridge RAMs. In conductive bridge RAMs, the first thing that we notice when we compare with VCRAMs is that the bottom electrode is still constituted of a noble material, gold, platinum, palladium, so on. However, the top electrode is what changes. The top electrode from being a passive noble metal is changed to an active metal. What is an active metal? It is something which can really oxidize easily. So it has low work function and very high diffusivity through this material. So some examples of such active metals is copper and silver. Next we will look at the nature of the insulating material. So here the insulating material is something called a solid electrolyte. What is the meaning of electrolyte? This terminology is coming from battery. A medium where there can be easy diffusion of ions is something known as an electrolyte. Here it is a solid electrolyte. Most of the times it is also a very simple metal oxide or a oxide or any insulating material. Finally, let's look at what is the nature of the filament in case of a conductive bridge RAM. And as the name suggests, it is a conductive bridge of metal atoms which have come out from your top electrode itself. So your top electrode had metal atoms which can easily oxidize. If they oxidize, they gain positive charge, they become metal cations, and they start moving to the bottom electrode, which has been given a negative voltage. And this solid electrolyte allows this diffusion to happen and this conductive bridge to form. But unlike VC RAMs, conductive bridge RAMs are inherently electrochemical processes. And this is what we will also see in the next class. So let us conclude today's class. In today's class, we saw why RRAMs are possibly very interesting candidates for storage class memories. We also saw the two key differences based on the nature of filament and creation mechanism of RRAMs, which is your valence change RAM and conductive bridge RAM. In our next class, we will do a deep dive into the physical mechanisms which makes valence change RAMs and conductive bridge RAMs operational. Thank you very much for your attention. See you in the next class.